Boom. All right, Julie, then we're back again. So, in this audio, we'll be discussing the fourth chapter of Chem 111. Yeah, and that is state of matter. The fourth chapter, state of matter. In the previous one, we saw hybridization, and of course, you remember everything discussed in hybridization. If you don't remember, you have to go back to the notes and get yourself acquainted to it, okay? Very important. So, next is state of matter. First, what is matter? Matter is simply any substance that has mass, not weight. Mass, not weight, right? So, matter is simply any substance that has mass and can occupy space. Now, there are basically three states of matter, basically, which are solid, liquid, and gaseous states. There are other states of matters like the plasma, like the Bose-Einstein condensate, and many other stuffs like that, which I just cannot mention. But basically, there are three states of matter, which are solid, liquid, and gas. And you have to understand the changes that occur due to different temperature. For example, solid can change to liquid, and that process is called melting. Liquid can change to gas, that process is called evaporation. Gas can change to liquid, that's condensation. Liquid can change to solid, that's solidification or freezing. Then gas can actually change its state to solid, and that's called deposition. Okay, while solid can change its state to gas, and that's called sublimation. And all these can only happen due to difference in temperature and pressure. Okay, so now among the above three states of matters, gases happens to be the best and the easiest state of matter to study and comprehend. Why? This is because they have similar properties with hypothetical gases called the ideal gas. They have similar properties with ideal gas. Ideal gases do not exist on a real note. They are hypothetical gases, gases that have just been designed to be, in quote, perfect gases, okay? But when you talk about real gases are the gases you know in chemistry: hydrogen, nitrogen, chlorine, fluorine, noble gases, they are called real gases. But when you talk about ideal gases are more or less like hypothetical gases. They are not real in their own. So they don't exist. They don't exist in any way. However, they have the following characteristics. Number one, there is no, I repeat, there is no intermolecular force of attraction existing between them. Every ideal gas has no intermolecular force of attraction existing between them. That's ideal. But a real gas definitely has intermolecular force of attraction existing between them. Secondly, ideal gases do not have volume. Come on, that's crazy. That's just hypothetical, because every real gas is known to have volume, and they occupy the volume of the containing vessel, right? Then thirdly, their collision with each other is perfectly elastic. Crazy, right? Perfectly elastic, meaning that ideal gases will collide with each other without even losing energy at all. That's the meaning of it being perfectly elastic, which is crazy, because every real gas, by virtue of collision, of course, their collision is perfectly inelastic, meaning that they lose energy during the collision process, right? And then the fourth characteristics of an ideal gas is that they follow the PV equals nRT equation in all conditions. That's ideal gases. They follow that formula, PV equals to nRT. However, as for real gases, they can only follow this condition under certain conditions. And the conditions are simple: at low density, low pressure, but at a very high temperature. That is when a real gas can follow this particular condition of PV equals nRT. We're going to come to that. That's the ideal gas equation. So you're going to understand that better. So all you need to know is that a real gas can actually become an ideal gas under certain conditions. And the conditions are simple: at a very high temperature, but a low pressure and low density. You may say that, but temperature and pressure are actually directly proportional. So how come that you can have a high temperature and a low pressure? That's crazy, right? That's chemistry for you. You can actually research on why it is so. So what we are saying in essence is that a real gas can later become an ideal gas. if only it can fit into these conditions. And take note, there is no standard temperature that can make every real gas behave as an ideal gas. Hydrogen, for example, at a particular temperature as high as maybe 100 degrees Celsius and a pressure of as low as maybe 1 atmosphere and a density of maybe 30 dm cube or 30 gram per dm cube, as the case may be, may decide to turn into a hypothetical gas. But oxygen may not do that within that same temperature range. So each gas has its own peculiar temperature range by which it can behave as an ideal gas, right? So, and that invariably means that the temperature must be high, the pressure must be low, and the density as well must be low for it to do that. So on that note, it will be wise for one to conclude that all hypothetical gases are not real gases. But real gases can become hypothetical gases. And the only condition they can do that is at high temperature and low pressure. And you see that in your textbook. Although your textbook has made a mistake, you can draw the students' attention to that. The textbook has it in record that hypothetical gases are gases, real gases can behave like hypothetical gases, that is ideal gases, at a very low temperature and high pressure. That's the reverse, and that's crazy. Don't let students learn that. So that takes us to the next stage, which is the variables used in gas behaviors. There are basically three variables we're going to discuss here, which are the volume, pressure, and temperature, right? So first, volume. The volume of a real gas is simply the size or the space occupied by the gas. And it is simply also referred to as the capacity of the vessel that the gas is contained inside. The SI unit of volume is cubic meter. But because cubic meter happens to be very big, other measurements have been adopted in the lab for easy measurements like centimeter cube, dm cube, liters, as the case may be. So, but they are not SI unit. They have just been adopted for convenience sake, right? Remember, 1 liter is equivalent to 1 dm cube. 1 dm cube is equivalent to 1000 cm cube, and 1000 cm cube is equivalent to 1000 milliliters, which is equal to 10 raised to the power minus 3 meter cube, right? So that takes us to pressure. Now, the pressure of a real gas is simply the force exerted by the gas per unit area. Yeah, force exerted on a gas per unit area gives you pressure. And the SI unit of pressure is in Pascal or Newton per meter square, right? Pascal or Newton per meter square. However, other measurements have been adopted for convenience, like the millimeters of mercury, the atmosphere, the Torricelli, the bar, and all that. It's important for you to note that 1 Pascal is equivalent to 1 Newton per meter squared. That means Pascal and Newton per meter squared are equal, right? Good. 1 atmosphere is equivalent to 1.01325 times 10 raised to the power 5 Pascal. Very important, which is simply 10 raised to the power 5 Pascal, okay? If you want to have it in an approximated version, 10 raised to the power 5 Pascal. And that is approximately 100,000 Pascal, right? Good. So 1 atmosphere is also equivalent to 760 millimeters of mercury. 1 atmosphere is also equivalent to 760 torr. So if 1 atmosphere equals 760 millimeters of mercury and 1 atmosphere equals 760 torr, that invariably means that 1 millimeter of mercury is equivalent to 1 torr. So you must be careful. 1 millimeter of mercury is equivalent to 1 torr. However, 1 atmosphere is also equivalent to 1 bar. Very important. 1 atmosphere equals 1 bar. And then also, it's important for you to know that 1 bar is equivalent to 750 millimeters of mercury. 1 bar equals 750, not 60 now, 750 millimeters of mercury. And then that is just that. So 1 atmosphere equals 1 bar and equals 1 Pascal and also equals 1 Newton per meter squared. Take note, the Torricelli was actually coined, the torr as a formula for pressure or unit of pressure was actually coined by a scientist called Torricelli, who invented the barometer used to measure atmospheric pressure. That is just an information. So that takes us to temperature. Temperature of a real gas is simply the degree of hotness or coolness of the gas. Its SI unit is in Kelvin. Yeah, in Kelvin, with its lowest temperature. We're talking about the ice point now. With its lowest temperature on a Kelvin scale called the absolute zero temperature. Yeah, that is the lowest temperature theoretically attainable by a real gas. The lowest theoretically attainable temperature by a real gas is referred to as absolute zero temperature. And its maximum temperature on a Kelvin scale is at the triple point of water, and which is 273.16 Kelvin. Then other SI units can be used, which are actually not SI, which are the degree Celsius, the degree Fahrenheit, and then the ranking, degree ranking as the case may be, right? So that takes us to the next part, which is the ideal gas laws. We have how many laws? 1, 2, 3, 4, 5, 6, 7 laws. Yeah, about 7 ideal gas laws. We're going to discuss 7 of them. So we start with the very first one there, and the easiest, which is the Boyle's law. Boyle's law states that the volume of a fixed mass of a gas is inversely proportional to pressure, at constant temperature. And that means P1 V1 equals P2 V2. However, it can also be defined in terms of density and pressure. That pressure, Boyle's law can be defined as follows: that the density of a given mass of a gas is directly proportional to the pressure at constant mass. Directly proportional to pressure at constant mass. That means pressure directly proportional to density, mass kept constant. You discover that the P becomes inverse to V, right? Good. So that takes us to Charles' law. Charles' law states that the volume of a given mass of a gas is inversely proportional to temperature. Did I say inverse? Sorry. Directly proportional to temperature at constant pressure. We can also define it as the density of a given mass of a gas is inversely proportional to temperature at constant mass. And by the time you do that, you discover that volume and temperature are direct in that relationship. So you will have V1 T2 being equals to V2 T1 as the case may be. And that takes us next into Avogadro's principle. Now, according to Sir Avogadro, he stated that the volume of a given mass of a gas is directly proportional to the number of moles of the molecules of that gas, right? So it simply means that number of moles and volumes are direct, and you can use them interchangeably at constant temperature and pressure. And that means you have V1 N2 being equals to V2 N1. Okay, remember, number of moles is given mass all over molar mass. So that takes us to the ideal gas equation. Now, the ideal gas equation can be derived by combining 3 laws we have stated above, which are Boyle's law, Charles' law, and Avogadro's principle, right? Now, remember, according to Boyle's, volume is inverse to pressure. According to Charles, volume is directly proportional to temperature. And according to Avogadro's, volume is direct to number of moles. So you see volume in all directions. So if you decide to take one volume, you discover that you're going to have volume being directly proportional to temperature and number of moles, but inversely proportional to pressure. And by the time you look for the constant of proportionality, K becomes R, and R is the ideal gas constant, which can take 2 values. The first value it can take is 0.0821 in liters atmosphere per mole per Kelvin, and can also take 8.314 Newton meters per mole per Kelvin. It can also be that in pascals, that's kilopascal. It can be in kilopascal per meter cube, kilopascal meter cube per mole per Kelvin. Now, how does it assume 0.0821? That is at STP. The volume of a gas at standard temperature and pressure using not SI unit right now, but using adopted units for convenience at standard temperature and pressure simply means standard temperature is 273.16 Kelvin. Now, the volume at STP is 22.4 dm cube or 22.4 liters, and then the pressure at STP is 1 atmosphere, and that is what we are calling STP. So at STP, 1 mole of a substance occupies 22.4 dm cube or liters. The temperature is 273.16 Kelvin and the pressure is 1 atmosphere. So by the time you do the mathematics, you discover that you have 0.0821 liters atmosphere per mole per Kelvin. Now, if you want to get the SI unit of these particular parameters at STP still, you discover that at STP, 1 mole of a substance will occupy 22.4, no longer dm cube, but becomes times 10 raised to power minus 3 meter cube as the volume. The temperature remains the same, which is 273.16 Kelvin. As for the pressure becomes in Pascal, which is either 100,000 Pascal or simply put 1.1325 times 10 raised to power 5 Pascal. Okay, then you just do the mathematics like that and boom, you get the answer 8.31, and that becomes in kilopascal per meter cube per mole, which you can later on convert to joules per mole per Kelvin, because energy is actually in Newton meters, right? Good. So that takes us to the next one there, which is Gay-Lussac's. But before we get into Gay-Lussac's, it's also important for you to know that you can actually derive another formula under this umbrella of ideal gas, which involves pressure, volume, and temperature. And that is P1V1 all over T1 equals P2V2 all over T2. Very important. And then also you can derive it further from the ideal gas equation, which is in terms of pressure, volume, and number of moles. So what will that be now? P1V1 all over N1T1 will be equal to P2V2 all over N2T2. Now you have a total of about 4 variables, no longer 3, as the P1V1 all over T1, right? Now it's 4 variables, 4 of them. Good. So that takes us to the almighty Gay-Lussac's. Now, according to Sir Gay-Lussac's, Gay-Lussac's law states that when gases, reacts, they do so in volume, which bear simple whole number ratios with one another and with the product, if gaseous, provided that temperature and pressure is kept constant, right? So that's a very simple definition, and it's always good to remember that. Take note, it only holds where gases are involved, okay? So the reactant and the products must have gases. When gases react, they do so in volume, which bears simple whole number ratio with one another and with the product, if gaseous, provided that temperature and pressure are kept constant, right? Now, for example, you can be asked that 10 cm cube of carbon dioxide is packed with 10 cm cube of oxygen. If all of these gases are measured at STP, calculate the volume of the residual gas after this pack. Volume calculation of residual gas undergoes certain steps, which I'm going to take you through now. First, write a balance equation of carbon dioxide reacting with oxygen to give you, carbon 2 oxide reacting with oxygen to give you carbon 4 oxide. And once you are able to do that properly, not carbon 4, please, carbon 2. Once you're able to do that properly, you calculate, you write their mole ratios. In other words, their reacting ratios, which is 2:1:2. Then the next thing is the volume before the reaction. Of course, you were told that it's 10 cm cube of carbon 2, and then 10 cm cube of oxygen. So you write that down, and then when you get to the side of carbon 4, you put a dash because it was not there before the reaction. So the next is the volume during the reaction. So during the reaction, they now have to share based on their ratio of combination, which are the moles, right? When gases react, they do so in volume. So you change the number of moles to volume. After all, Avogadro said so. So what happens now is, since you were told that 10 cm cube of carbon 2 was packed with 10 cm cube of oxygen, so that simply means that a 10 cm cube will be equivalent to 2 moles. Now, 1 mole of oxygen partook in the reaction. That simply means that 5 cm cube will be used out of the 10 cm cube of oxygen inside the vessel. And then, of course, because there are 2 moles of carbon 4 produced, simply means that 10 cm cube of carbon 4 will be produced. Then at the end of the day, you look for the unreacted gas, the volume of the unreacted gas, by subtracting 10 cm cube of carbon 2 minus 10 cm cube of carbon 2. That means carbon 2 becomes totally used up. And then 10 cm cube of oxygen minus 5 cm cube of oxygen, that gives you 5 cm cube. And then the carbon 4 produced is also 10 cm cube. So the unreacted gas is 5 cm cube of oxygen, while the residual gas becomes the algebraic sum of the unreacted gas and the gas produced, which is 15 cm cube. Now take note, if you decide to swap variables like oxygen coming first and then carbon 2 coming later, you may not just get the same answer. In fact, you will not get the same answer. So it is always best to make use of the limiting reagent. Which of the reagents will be completely used up first? And from this reaction, it is clear that carbon 2 oxide is the limiting reagent. So it will take the lead in terms of distributing volume during reaction. Limiting reagents are those reagents that gets completely used up, that once they are completely used up, no further product can be produced. So in this reaction, carbon 2 is the limiting reagent. How did I manage to know that? You will see that in second semester. All right. So next is Gay-Lussac's law, which is also called pressure law. Gay-Lussac is also referred to as Al-Montan's law, right? It's actually Guillaume. I think Guillaume. That's Guillaume. Guillaume Al-Montan's law. So if you hear Al-Montan's law, remember Gay-Lussac's, right? So Gay-Lussac actually coined pressure law as well. And pressure law states that the pressure of a given mass of a gas is directly proportional to temperature at constant what? At constant volume. And that's pressure law. And that's also referred to as Al-Montan's law. So that takes us to the next law, which is Dalton's law of partial pressure. According to Dalton's law of partial pressure, the law states that in a mixture of gases that do not chemically combine together with one another, that the total pressure exerted by the gases is the algebraic sum of the partial pressure of the individual gases that makes up the vessel or the system, as the case may be. So total pressure is the algebraic sum. Imagine in a vessel I have 3 gases, A, B, and C. The total pressure in that vessel is the pressure exerted by each of these gases. The pressure exerted by A plus the pressure exerted by B plus the pressure exerted by C. Total pressure. And at times you may be asked to calculate the total pressure when you are given volume, you are given temperature, you are given number of moles, and probably you're given ideal gas constant. So you can always do that to calculate the total temperature, right? So it can just come in a dynamic way. You just have to be smart and thinking. So total pressure becomes the pressure of A plus pressure of B plus pressure of C. Now, the partial pressure of the individual gases can, however, be computed by multiplying their mole fraction with what? With the total pressure of the system. Get the mole fraction of gas A and multiply it by the total pressure. That will give you the partial pressure of A. Now, what is the mole fraction of A? The mole fraction of A simply means the number of moles of gas A all over the total number of moles in the system. Number of moles of gas A all over the total number of moles in the system. That gives you the mole fraction of gas A. If you are looking for the mole fraction of gas B, is the number of moles of gas B all over the total number of moles in the system. So multiply that by the total pressure, that gives you the partial pressure of B. Another thing you need to take note of, when a gas is collected above water, such gas is likely going to be saturated with water vapor. And hence, the partial pressure of such gas is simply the difference between the total pressure on the system and the partial pressure of the water vapor. That will give you the partial pressure of the gas collected above water, because it's going to be saturated with water vapor. So for you to get rid of that water vapor, subtract the total pressure from the water vapor. That gives you the pressure of the gas. You get it? So one can comfortably say that the partial pressure of A becomes the total pressure minus the water vapor pressure. Simple. Walk away. And that takes us to the last law. The last law. And that is Graham's law of diffusion, aka Thomas Graham's. That Buncan Thomas. Now, Graham's law of diffusion actually is also the same as Graham's law of effusion. That simply means that there is a difference between diffusion and effusion. There's a difference, a slight difference. When you talk about diffusion, the law of diffusion occurs in an open interface, an open space, while the law of effusion occurs in a very small pinhole, in a very small opening. Imagine a gas passing through a filter, a merge, and another gas just wallowing in open space. Their speeds are not going to be the same, because one has restriction, the other do not have restriction, right? So the ones with restriction is the law of effusion. The ones without restriction is the law of diffusion. So according to Thomas Graham's, the law of diffusion or effusion states that the rate of diffusion or effusion of a gas is inversely proportional to the square root of its density at constant temperature and pressure. That simply means that rate of diffusion inversely proportional to what? To the square root of density. And by the time you do the mathematics properly, you have R1 root D1 being equals to R2 root D2. And of course, you will like to make some derivatives here. We tell them that but density is mass over volume. And from the ideal gas equation, PV equals nRT, make N the subject of the formula such that N is measured in mass over molar mass, and then arrange your formula such that you have volume over mass, which is density. And by the time you are able to do that, you will have density being directly proportional to molar mass pressure and inverse to the ideal gas constant and temperature. So you can just select density and mass, which is the molar mass. And what you're going to have at the end of the day is that density is directly proportional to molar mass, right? So now that density is also directly proportional to molar mass, it will not be out of place to say that the rate of diffusion or effusion of a gas is inversely proportional to the square root of density, and as well inversely proportional to the square root of the molar mass of the gas. So it's not going to be out of place. And by the time you do the mathematics properly, you will have R1 all over R2 being equals to the root of D2 over D1 being equals to the root of M2 over M1. However, when two gases are involved, let's say gas A and gas B are involved in the process, the first gas and the second gas, you can invariably say that the rate of the first gas all over that of the second is equal to the root of the density of the second all over that of the first should be equal to the root of the density of the second, the mass of the molar mass of the second all over the density of the first, And also take note that the rate of diffusion is equal to the volume of diffusion all over the time taken. That's another thing. Volume of diffusion all over the time taken gives you rate of diffusion. And then by the time you take the volume to be constant, rate of diffusion is simply the reciprocal of the time. And you can bring it into play. If rate is inversely proportional to time, that means R1 all over R2 becomes T2 all over T1. And you can even equate it to density and molar mass to become D2 all over D1, that's the root, being equals to the root of M2 all over M1. Also take note, density is simply half the relative molecular mass. So basically that is that. However, this can go as a hint. Assuming you are given a question and you are told that 100 cm cube of nitrogen diffuses in 20 seconds, how long will it take for 50 cm cube of chlorine to go through the same diffusion process? Now, if you check, their volumes are different. The law demands that you bring their volume, make their volume constant. If 100 cm cube of nitrogen diffuses in 20 seconds, how long will it take 50 cm cube of chlorine to diffuse? So you have to step down the 100 cm cube of nitrogen into 50 cm cube. How? By asking yourself a question of simple proportion. If 100 cm cube of nitrogen diffuses in 20 seconds, then 50 cm cube will diffuse in how many seconds? By the time you get that time, you can now apply the law of Graham's to work with chlorine, knowing full well that they are now at the same volume. And you just get it right and walk away. So, Julie Ben, that is that for this chapter. We have done justice to this chapter. And I think it's high time we move to the next. Boom.